Okay, good morning and welcome back to the study of first order equations. So, in the last classes few classes we were discussing about the first order equation in two variables and we considered the case for linear equations and quasi linear equations and we have introduced what is known as characteristics and we have introduced the concept of characteristic. Now, in this lecture we will do the same thing for the general nonlinear equation with two independent variables. So, a general equation in two variables looks like that f of x y u ux uy equal to 0. So, we introduce some notation which is a customary notation. So, we will have p is equal to u x, q is equal to u y and sometimes frequently we u also equal to u z is equal to u. So, in the algebraic form you can write this equation f x y z p q is equal to 0. So, the geometry is more hard, that is the first thing. Geometry is hard. In the quasi linear case you will have seen that f of x y z p q is equal to a u a p plus b q minus c, that is what f x y, where a is equal to a b c etc. are functions of x y is a function of, so a is a function of x y z and it is linear in p and q, similarly b, similarly c. The thing is that if you recall the quasi linear equations, ABC is the in quasi linear case, in quasi linear ABC gives characteristics directions, okay. That is what we have seen it. But the one of the difficulty now here, the characters here, the characteristic directions are not visible. So, we have to find out that directions are not visible, okay. That is a difficulty here, okay. So, we need to do something more about the geometry of that one, but then there are more difficulties. There may not be existence, you may not be able to solve. So, like the equation, suppose you need this to solve p square q square plus 1 equal to 0, no real solution, because you cannot find something square plus 1 equal to 0, no real solutions. There is also a difficulty, there may be lack of uniqueness. I am talking about initial value problem. Okay. For the given initial value problem, all these things can happen as you see in this example, okay. And there are more geometrical objects, like Monge cone, which I am going to introduce. Monge cone, Monge's characteristics strips etc. So, you have to do such kind of geometry. However, the initial value problem is similar, initial value problem is same as earlier. For example, what is the initial value problem? You have a domain in xy space and you have a domain here omega, and then on that you have an initial curve gamma naught. Then what you look for is that you look for a characteristic. So, you have a lifted initial curve gamma naught bar, and you look for a surface z equal to u x y, that is what is called the integral surface. These are the things we have done. So, we have to exactly find a characteristic surface passing through a lifted initial curve. So, as far as the initial value problem is concerned, there is no issue. Okay. So, what is the difficulty? So, let us understand the geometry little bit. Geometry. So, you fix a point x naught. So, let us try to understand, fix a point x naught, y naught, z naught in R3. Okay. And look at this equation, f of x naught, y naught, z naught, p and q. Think it as a function of these two variables p and q. So, this will provide, this is one equation in two variable, one equation in two variables, variables p and q. Okay. Thus, in principle, assume that you can solve it. So, solve, you know the conditions under which it can be solved, solve q in terms of p. Assume that there is a unique solution. So, need not be, there may not be a solution like you have seen p square plus q square plus 1 is equal to 0. So, given p you may not be able to find a like that q square which is minus, but assume that there is a solve, in fact assume that you can solve it uniquely, that is also need not be correct all the time. So, but since we are trying to understand the geometry, try to say that there exists a solution, there exists a unique solution for q. So, every p there is a q by solving this non-homogeneous equation, okay, this algebraic equation, sorry. So, let us write z naught is fixed. So, we will not write again and again. So, you will basically have, so that implies f of x naught, y naught, z naught and p and q you solve it as in terms of p. So, this is a one parameter family. So, given any p, so you have to understand that. So, you have a point here. So, you think it as an integral surface. If it is an integral surface z equal to u x y, if you take a point x naught, y naught, z naught, imagine this geometry. So, in this case if you are working on a x naught, y naught, z naught is an arbitrary point, but if you take x naught, y naught, z naught and if you think that these are all known its derivative, this is its normal, p q minus 1 is the normal. This was the picture again. So, once you have a normal, there will be a tangent surface. So, you have a tangent plane, one parameter family tangent plane, one parameter family of tangent planes, one parameter family of, and what is the equation of this plane a into. So, if you take a point x naught here, so you take a point x y z here. So, you have x minus x naught, this is a direction. Okay. So, you are when the equation of a plane passing through x naught, y naught, z naught and whose normal is p q minus 1, and then it's the tangent plane is given by p into x minus x naught plus q into y minus y naught equal to z minus z naught. Okay. So, you have two equations which is a one parameter family, because q you can think it as a q, you view it as a function of p. So, you have a one parameter family of tangent planes. So, just imagine now the geometry. So, you have a point fixed x naught, on that point you have a plane, that is equation of a plane. So, when you have a plane and p changes, you will have another q, you have another tangent plane. So, there will be a planes, there will be planes passing through this point as p changes, you get a one parameter family of planes, and it will if you look at its envelope or this one parameter family of planes produces a cone, a generalized cone, need not be a right circular cone. So, this will give you, so the geometry is that for each point your equation f x naught y naught z naught p q produces a cone, and if the point varies you get a field of cones. So, this gives you a field of cones, you get that, right. So, you have a plane for fixed p, you have a q and you have a plane. As p changes you will have a family of planes, one parameter family of planes all passing through x naught y naught z naught, it produces a cone. So, you get that thing. So, what will happen is that for every point you will have a cone, you take the point, so you will have a cone. So, let us imagine little more about the geometry. So, these are called the Monge cones, Monge cones. So, what will happen if it is a tangent plane, you want this plane to be a tangent plane. Equivalently you are looking for a surface. So, essentially what you are looking for, so if you are looking for an integral surface, each point you want this cone to be a tangent to the integral surface. So, if you can produce a surface in such a way that at each point the Monge cone is tangent to that surface, then that surface will become an integral surface. The converse is also true. So, you are basically looking at a line of contact between that will give you the characteristic direction. So, looking for the Monge cone and then looking for its your surface at each point, it will be tangent to the Monge cones. So, let us try to write down the equations of Monge cones, equations of Monge cone. So, let me write down all the equations. You have your equations f x naught. So, these are the three equations f x naught, y naught, z naught, p q equal to 0. You solve this and then you will have x minus x naught into p, this is the equation of the plane, plus y minus y naught into q equal to z minus z naught, and then you have so these are the two equations, you get it. Okay. So, you want to find its envelope, the line of contact, envelope or and line of contact. How do you do this one? To do that one, you view these are all functions of p and q. So, differentiate with respect to p, with respect to p. So, the first equation f x naught y naught z naught, if you differentiate with respect to p, you will get f of p plus f of q into dq by dp. You are viewing it as a function of p, that is equal to 0. If you differentiate the second equation with respect to p, you get x minus x naught plus y minus y naught into dq by dp is equal to 0. So, you have two equations for the. So, these two equations together with these equations basically, so you eliminate now. So, eliminate dq by dp. If you eliminate dp by dq, you get this will give you. So, let me use a different color. You eliminate dq by dp, you get x minus x naught by fp is equal to y minus y naught by fq. So you see, so you have these two equations star together with plus u star plus this equation. So that will give you your equations of Monge cone, and these two equations x minus x naught p plus y minus y naught q equal to z minus z naught together with this x minus x naught by fp will give you the line of contact. So I will combine that. If you combining, this will implies you get this equation x minus x naught by fp is equal to y minus y naught by fq is equal to, I can multiply and do that one, you will get p into x minus x naught, I can write this, plus q into y minus y naught. So I am multiplying and dividing. This is standard thing which you know it, you can do that. This will be equal to q fq. But what is p into, if you go to the free page, p into x minus x naught, all these will be z minus z naught by 10. So this will be same as z minus z naught by p fp plus q fq. This is nothing but the equation of line, right? These three things are together is the equation of the line of contact. Line of contact. You see? So you got it. Now look at one more thing immediately. So if you look at this tangent plane, so let me use a different color. So look at the tangent plane. So you have a tangent plane, you have your x minus x naught y naught z naught, and then you have x y z in the tangent plane, and you have your, this is your tangential direction, this is your characteristic direction, and this equation tells you immediately fp fq p fp plus q fq has the same direction as x minus x naught y minus y naught z minus z naught. That means fp fq p fp plus q fq gives you the characteristic. This implies the is the characteristic direction. Once you get the characteristic direction, you can immediately introduce your characteristic curves. So I will do it in the characteristic. So introduce characteristic curves, and then we will see the difficulty. Your dxt by dt equal to f, these are all functions of t, is equal to fp dy by dt at t equal to fq, and dz by dt is equal to pfp plus qfq. So what are the difficulty compared to your quasi-linear case? So what was in the quasi-linear case? So I am comparing, so you will understand the difficulty. Quasi-linear case, fp was a, which is a function of x, y, z, and fq was b, which is also a function of x, y, z, and pfp, you can compute this, pfq plus qfq is equal to c. You can verify all this. So that shows this was a complete system. But here what is the difficulty? It was a complete system. This one, it was a complete system. Difficulty here Fp, Fq etc. Pfp plus Qfq may also depend on P and Q may depend on P and Q, and hence star need not be a complete system. Be a complete system. And this also suggests you need equations for P and Q. So, need equations for P and Q that we can derive easily. P and Q, how do I derive? Because P is equal to P of x t y t, right. Q is equal to Q of x t y t. P of x t y t. So, if you differentiate, you get two more equations. dP by dt is equal to Px into dx by dt, that dx by dt is equal to Fp plus Py into Fq. Similarly, dq by dt is equal to Qx Fp plus Qy Fq. So, you have now two more equations. Earlier you already got three equations, x dx by dt, dy by dt, dz by dt. Together with now you have 5 equations. I will tell you the geometry. You should not think it is a curve in R5, because our working space is R3 only. So, you should not be seeing it is a curve in R5. Still the characteristic curves you have to see it as a curve in R3 only. But what is this Pt and Qt you are, but you are, that shows that you are unable to solve xt, yt, zt completely. You have to solve xt, yt, zt together with its pt, qt, xt. Okay. But before that, the difficulty is that this px and px, qy are second order, and that is undesirable, right. For example, because P is equal to Ux, so Px means Uxx, undesirable. You do not want that second order, because you are dealing with the first order equation and you do not want second order terms coming into, second order derivatives coming into the picture. Somehow you have to eliminate Px and Qi, which you can do it. So, eliminate, you have to eliminate. I will not give you the details, you can work it out the details. You write down, differentiate the equation fxy, differentiate fxy z pq with respect to x and y. If you differentiate, you get fx plus fz, you differentiate fz into p plus Fp into Px, Fq into Qx equal to 0, and similarly you differentiate Fy, you get Fz again into Q, and okay, and Fp into Py plus Fq into Qy. So, you have to eliminate 4 quantities Px, Py, Qx, Qy. You got 4 equations, but you need one more equation, that you can easily check that Px equal to Qy. right. This is also true, P x equal to, because P x is equal, this is equal to U x or P y is equal to Q x, I think. So this is P y equal to Q x. So, this is nothing but U x y, this is also U x y. So, you have 5 equations, eliminate and you can write down the equations now. So, this will imply, by eliminating, it will imply your dp by dt is equal to minus f of x minus f of zp, and then you will have your dq by dt equal to minus f of y minus f z. So, you see you have 5 set of equations, but how do you solve it and what is the geometry? So, I want to get what is the geometry now. Okay. So, you have a curve, characteristic curve, you want to do it, you are not able to solve it, x t y t z t. You want to solve x t y t z t together with p t q t, but p t q t minus 1 is a normal. So, you have to view this one. So, you are not only solving the curve x t y t z t, you are also solving the normal. When you are solving the normal, which is equivalent to saying that you are actually solving the tangent plane. So, each point you are solving for the tangent plane also. Okay. So, you have to solve for every curve like that. So, okay. So, you have these things. So, every curve you have to do that thing, but then to solve that you need 5 initial conditions, but you are given only 3 initial conditions. So, you have to create 2 more initial conditions, and these are called characteristic strips. Characteristic strips. So, let me tell you once more how do you. So, you have your lifted initial curve. So, you have your lifted initial curve. So, let me do it in the different color. So, you have your gamma naught bar, that you know this is nothing but x naught of s, y naught of s, z naught of s. You have that. On this point you want to solve characteristic curves, then you can have the same procedure as in, but to solve characteristic curve you also need to solve these things together. So, you have to solve not only the characteristic curve, you have to solve the tangent plane. So, similarly, if you want, then you need initial strip, basically you need to have initial strip. Okay. So, in other words, we need to get, you can need to get your initial conditions P naught of s and Q naught of s. This cannot be imposed, you cannot impose these conditions. You say that in the problem it should be given, no, cannot impose, you have to derive that, cannot impose, and that is what you are doing. How do you do that one? So, first thing is that you need 2 conditions. Now, you have to solve for P naught of s as well as Q naught of s, right. You have x naught of s, y naught of s, z naught of s, but the characteristic curves are solved for x t, y t, z t together with p t, q t. So, you need initial conditions for P naught of s and Q naught of s, but the initial curve lies also on the equation, that also satisfies the equation, because it lies on the lifted initial curve lies on the characteristic integral surface. So, that implies f of x naught of s, y naught of s, z naught of s, P naught of s, Q naught of s equal to 0. So, Of course, whether it have a solution etc., you need is a different issue. And so there is one more condition. So you need one more equation, that is called the strip condition. All this you have to know. Strip condition. What is strip condition? You have your uxt is equal to lies on right. Let me come to the strip condition. Z is equal to, so you have generally Zt is equal to u of xt yt, right. So if you differentiate this with respect to t, you will have dz by dt is equal to ux which is you will do, which is p. So you will have p into dx by dt. This is pt, it is satisfied for every t, plus qt, that is uy into dy by dt. This strip condition is satisfied not only the characteristic can. So the strip condition, this implies this strip condition dz by dt equal to etc. also satisfies the initial curve. So you will get one more condition for your initial p naught of s, q naught of s. That means you will have your z naught of s, that is nothing but your dz naught by ds. This is also satisfied at s is equal to p naught of s into dx naught of by ds. This is along the initial curve, plus q naught of s into dy naught by ds. So you have two equations. These two equations will give you p naught of s and q naught of s. See? So in principle, if you look at it, you have 5 equations. If you go for 3 equations for xt, yt, zt, then 2 equations for pt, qt, 5 equations, and then that 5 equations you have to solve it to get the characteristic strips. Then 3 conditions for initial conditions are given and 2 initial conditions are, if all this can be solved. So that is where when you do a particular problem, you may face difficulties. It is not that always this can be solved, but then you can apply this method. And if you look at it, all these things, what you see is that you are only solving ODE. So the message is that to get the solutions to your PDE, you are actually solving ODEs. So let me complete this talk, this particular talk, by giving the final theorem. So you define x naught, these are all has to be smooth, y naught, z naught, okay, p naught, q naught are smooth. There are very precise conditions. If you want to get a very precise condition, look into our reference book and assume your characteristic condition. Assume non-characteristic condition. It is a non-characteristic. You do not want to be a characteristic. Non-characteristic condition. This is the condition for solvability. dy naught by ds. Instead of a in the Cauchy linear case, you have fp. It is in everything in x naught, etc. Minus dx naught by ds into fq x naught, etc. This should be non-zero. This is along the initial curve, lifted initial curve. Then implies there exists not unique solution, there exists a solution. There is no uniqueness. So I will end this talk with showing an example. This theorem can be proved along the similar lines as in the quasi-linear equation. Example. So, you look at this equation, p square plus q square minus 1 plus that is the PDE is ux square plus uy square equal to 1. Okay. So, this is an exercise which you can work out. There are more exercises in the book. I suggest you go through and do some problems. Okay. And you can see that you can get two solutions. uxy is equal to plus or minus 1 by, and what is the initial condition? Initial condition. So, the initial condition equal to u equal to 0 on x plus y equal to 1. This is your initial condition. So, you can see that plus or minus 1 by root 2 x plus y minus 1. This is your PDE, this is your two solution. The reason is that when you solve for q in terms of p, you get two solutions. You see, you do not have a unique solution. So, for each p you get two separate one parameter family of planes, deriving that two different surfaces leading to two integral surfaces passing through the same initial curve. But up to quasi-linear equation there was a unique solution passing through that. So, with this I will end my talks on first order equations in two variables, but you will now listen later from the higher dimension multi-variable case from next lecture on in another 2 hours or something. You will we will introduce you the similar concepts, but this kind of easy or simple geometry may not be available, but geometry is still there. Understanding the hypersurfaces in Rn plus 1, you have to look for solutions the surfaces in Rn plus 1, just like two variable you look for surfaces in R3, there you look for surfaces in is something like hypersurfaces in R3. Thank you.